whereas as far as I know, so this isn't sort of perfect information, but this is much more information than there was before. As far as I understand, basically nothing is known about the explicit form of the H moduli space. And so with this kind of technology, you actually learn something. And the thing that you learn, if I would summarize it in sort of a slogan, what happens is that what this metric looks like is you start with a kind of very naive looking metric, so-called semi-flat metric. So this space, if I actually draw the Hitchin space, what the Hitchin space looks like is it's a kind of torus vibration over some base. So we have the base B, the same B that has appeared. Oh, no, it's not the same B. Was B the whole space of stability conditions for you? Okay. B is this Lagrangian subspace, this half-dimensional Lagrangian subspace of the space of stability conditions. In this case, it's the so-called, if the Hitchin base is the space of these spectral curves. Yes, right, that's what I said. B is just the space of these spectral curves, the space of these differentials. And over that, you have a torus vibration. The whole thing is this M. And what the metric on this torus vibration looks like is there's a sort of naive first approximation to it. It depends on a parameter. You can change the parameter so that the tori are shrinking down very small. In that limit, where the tori are shrinking down very small, there's a sort of naive first approximation to this metric where it's just totally flat on the torus fibers. It has isometries, just U1 squared isometries, or U1 to the 2R isometries. It looks like a totally just trivial thing. And that approximation is fantastically good everywhere except at the singular points where the torus fiber degenerates. Those would be the places where two quadratic differentials are, where two zeros of the quadratic differential are colliding. Around those places, the torus fiber is degenerating, and so you can kind of see that this isometry has to be broken, right? Because it shrinks at a particular place. So the isometry has to be broken by something. And so what breaks it are corrections to that naive semi-flat metric. And the corrections are weighed exactly by, they come exactly from these discontinuities. So the sort of naive metric is what you get if you just forget all the discontinuities. When you put the discontinuities in, you get some kind of quantum corrections to the metric. And those quantum corrections have the effect of destroying the isometries of the thing, and on the other hand, smoothing out the bad behavior near the singularities. So it's a kind of appealing sort of physical picture of what the metric on these hyperregular spaces look like. So the slogan is that these special trajectories of quadratic differentials, they have sort of another use in life. They're actually imprinted in the metric on the Hitchin moduli space. If someone gave you the Hitchin moduli space and you had a sufficiently good microscope, you could read out the numbers of these special trajectories for k equals 2, and for higher rank, you would read out these more complicated kind of networks. So they're fundamental objects also in that way. And from that point of view, the wall crossing formula also plays a role. The role of the wall crossing formula is to guarantee that this metric is actually a smooth metric. Okay, I think that's it. Yeah, I'm done. Thanks, this was really fun.